Hi guys, can you guys hear me?
Yes.
Okay, I'm going to wait few more minutes so few more people can join and then I'm going to go start the lecture. All right, so I'm going to start the lecture for today. I'm going to start by repeating the announcement that I made on Web Campus. So what I am going to do is instead of curving the exam score, I'm going to curve the midterm score. So um, this midterm score is a score letter grade that I have to report on my UNLV. Before it goes on to my UNLV, I will post it on Web Campus first. Okay, you will see the percentage where you're standing in the class, and then the letter grade for the midterm grade. Okay, so yep, that's what I have decided to do. Instead of curving the exam grade, I'm going to curve the midterm grade. Okay, again, if you're falling behind, um, of chapter 14 and chapter 15 material, make sure you catch up those materials because these chapters will be on final exam. Okay, and then if you receive um, low score for the first exam, schedule an office hour with me, talk to me. I will go over the exam with you and then explain to you where you, which specific section or part you have to revisit and study more thoroughly. Okay, so yeah. Um, and then I have posted some recommendations regarding how to prepare for the exam, how to study for this course. Okay, so read those things thoroughly. The two most important things are creating your own study guide. Okay, this is very important because by paraphrasing, okay, and paraphrase through the paraphrasing, making your own study guide, you can check and see if you yourself really understood the material. Okay, if you don't understand the material, you can't really paraphrase, you can't really make your own study guide. Okay, so the only way to make this material really uh, in order to make this material your own, you have to be able to paraphrase and make into your um, own writing. Okay, so uh, create your own study guide. If you did not prepare a study guide for exam one, I recommend you do that now because that study guide is what you're going to be using for the final exam. Okay, you don't want to wait until final exam and then go back to chapter 14 and 15 material and create first exam study guide. Okay, so yeah, this is a good time for you to look back chapter 14, chapter 15, prepare a study guide, and then another thing I recommended was resolving the sample exercises. So the sample exercise that I solve in the class, make sure you resolve them at least 3 times. Okay, by that means You have to have a blank piece of paper. Don't look at the answer. Just by looking at the question and just by along with the equations that you have memorized on top of your head, try to solve and see if you can how far you can go. Okay, and then compare your answer with the answers, correct answers on the lecture note. Okay, in this way, on the exam, when you see a similar question, you know what equations you're supposed to use. Even if you have all those equations memorized, if you're not familiar with where to use those equations, then it's most likely you're not going to be able to utilize the equations that you have memorized. Okay, so and then after creating your own study guide, resolving the sample exercises 3-4 times. If you're still lost, if you're stuck, then schedule an office hour with me. I'll love to help you. Okay, and if you want to check and see, check your version of study guide with me. I would love to go over the study guide with you. If you're missing anything or if you need anything extra, I will provide feedback regarding your study guide. Okay.
Dr. Lee, quick question. Did you send out the questionnaire that you wanted to know from us, like the survey?
Yeah, so the survey was about the study guide, my study guide. So I was wondering if it was helpful or not. If it's if it's not particularly helpful, I'm just not gonna make it for the next exam because um, it was a time-consuming thing for me too. But if it was helpful, I would love to make it for you guys. Okay, but if it wasn't that helpful, then I'm just gonna focus on making the the sh- the sh- I will prepare one sheet that contains all the things that you need to memorize. So I'm just gonna make that memorization chart. But if you guys think the study guide is helpful, then I will continue making it. The survey is already on Web Campus since last week. Go to the quiz section, and there the survey is right there.
Okay, thank you.
Mm-hmm. All right. So let's continue chapter 16. Last week, we have learned about basic concepts of acids, bases, conjugate bases, relative strength of acid, and we've also learned about how some compounds can be amphiprotic. Okay, meaning amphiprotic meaning can a compound that can act as both acid and base depending on the chemical environment. Act as both. Okay. So water is an amphiprotic compound. Under the presence of acid, water can act as a proton acceptor. So water can accept proton from acid. Under presence of base, water can act as a proton donor. So water can donate its proton to the base. Okay? And in fact, one water molecule can donate a proton to another water molecule. That's what you're seeing over here. Between the water molecules, there can be proton exchange. The reaction between these two water molecules producing two ionic species, this is called autoionization of water. Okay. So in this reaction, one water molecule is acting as a Bronsted-Lowry acid, donating a proton, donating this proton. Okay, it's actually, this is going to, the oxygen is going to steal the proton from acid. Okay, so acid is donating the proton. So one water molecule is acting as a Bronsted-Lowry acid here, donating a proton. The water molecule is acting as a Bronsted-Lowry base, receiving a proton. Okay, so in producing hydroxide and hydronium ions. This forward and backward reaction occurs extremely fast. And water molecules actually don't remain ionized for too long. Only about 2 out of 10 to the 9 water molecule are ionized at any given instant. Okay, so therefore pure water contains almost entirely of water molecules, and because discharged ionized species are not observed that often, water is a poor conductor of electricity. Okay, pure water contains entirely of water molecules rather than ionized species. And therefore, pure water is a poor conductor. Okay. So, okay, so although concentrations of hydroxide and hydronium found are very low, this is an equilibrium reaction where reactions in both directions are occurring simultaneously. Since it is an equilibrium reaction, we can write the equilibrium expression for this reaction. The equation for Kc, equilibrium constant, is, do you guys recall? Product concentration over reactant concentration. Okay, raised to the power equivalent to the coefficient in the balance equation, right? So the Kc equilibrium constant is product concentration over reactant. So technically it should be hydronium ion times concentration of hydroxide divided by concentration of water. However, the reactants are pure liquids. So you're not supposed to include pure liquids in the equilibrium expression. So pure water is going to be excluded from the equilibrium expression. So the Kc for this reaction is only going to be concentration of hydronium ion, hydronium, and concentration of hydroxide. This special equilibrium refers specifically to the auto-ionization of water, is denoted as Kw instead of Kc. W stands for water. This is the equilibrium constant for auto-ionization of water. Okay. At 25 degrees Celsius, the Kw is experimentally found to be 1 times 10 to the negative 14. This is a value that you need to memorize. Okay. What can you tell from this case Kw value? Is it larger than 1 or smaller than 1? It is 10 to the negative 14, that means it is extremely small. It is way smaller than 1. Since this is way smaller than 1, we know that at equilibrium, the reactant dominates. Mostly we have water molecules. And the product concentration is very low at equilibrium. Lower than 1. So that means at equilibrium, the reactant dominates. Okay? So you have more water molecule than the ionized species. That's what this equilibrium constant is telling us. So in the next slide, we will learn why these concentrations of hydronium and hydroxide in the aqueous solution is important. Here, the concentrations of hydronium ion and hydroxide ion in the aqueous solution is important because it can tell us whether the solution is neutral, acidic, or basic. Okay? Water, pure water, is a neutral solution, which has equal concentrations of hydronium and hydroxide ion. Okay? Again, okay. Note that the proton and hydronium ion can be used interchangeably to represent the hydrated proton. So we can replace the hydronium ion for proton. So it's written as proton here. So using water as a standard, we can compare the concentration of proton and hydroxide in the aqueous solution to determine whether a solution is acidic, basic, or neutral. If a solution has proton concentration higher than hydroxide concentration, the system is considered acidic. If the solution has hydroxide concentration higher than proton concentration, the system is considered basic. And one thing to note is that the Kw value the equilibrium constant for the autoionization of water is of neutral solution is applicable to acidic solution and basic solution. So Kw value is always 10 to the 1 times 10 to the negative 14 for all three solutions. Okay? So let's try a sample exercise. I'm going to read the question. Calculate the values of proton and hydroxide concentrations in a neutral aqueous solution. So neutral aqueous solution. It is a neutral solution. From the last slide, we know that for neutral solution at equilibrium, the concentration of proton equals to concentration of hydroxide ion. So what is the exact numerical values of these concentrations? Let's find that in this example exercise. Let's start by writing the Kw expression. So the Kw is proton concentration times hydroxide concentration. Since we don't know these concentrations, we're going to represent it by writing X. Okay? X times X. Because their numerical values equal to each other. This is what we already know for the neutral solution. Okay? And since we already know the Kw value of the neutral aqueous solution, that it's 1.0 times 10 to the negative 14, now we just have to solve for X. X is going to be square root of this the kW value, and it is going to be 1.0 times 10 to negative 7. Okay, so that means in neutral aqueous solution, concentration of proton equals to concentration of hydroxide equals to 1.0 times 10 to negative 7. Molar. Let's try another sample exercise. Calculate the concentration of
Can you go back really fast?
Oh, sorry.
It's okay. Thank you. Oh, okay.
Let me know when you're done.
I'm done. Thank you.
Okay. All right. Calculate the concentration of proton in solution which hydroxide is 0.010 mole. B, a solution in which hydroxide is 1.8 times 10 to negative 9 molar. Okay, we're going to assume that the temperature is 25 degrees Celsius. So in this question, the concentration of hydroxide ions are given and we are asked to find the proton concentrations. Since we already know the Kw value, we can simply plug in the given hydroxide concentrations value to find out the unknown proton concentrations. Okay, so for A, Kw is proton concentration times hydroxide concentration, which is equal to 1 times 10 to negative 14. Okay. Then concentration of proton is going to be Kw value divided by hydroxide concentration. Which is 1.0 times 10 to negative 14 divided by 0.010. We have 1.0 times 10 to the 12 molar. Okay. So, is this solution acidic or basic? If you compare the concentration of base versus acid, we know that hydroxide concentration is way higher than acid concentration because hydroxide concentration is larger than proton concentration. This solution is basic because concentration of hydroxide is larger than concentration of proton. Moving on to question B, just as in A, in order to find the proton concentration, you will take the Kw value divided by concentration of OH, which is 1.8 times 10 to the negative 9 equals to 5.6 times 10 to the negative 6 molar. Okay, all right, so is this solution acidic or basic? The OH concentration is this, acid concentration is this. This solution is going to be acidic because concentration of proton is higher than concentration of hydroxide. Acidic solution because concentration of proton is higher than concentration of hydroxide. Let me know if I'm scrolling too fast. Let me know if I have to stop, okay? So, as we have seen, the concentration of proton and hydroxide are very small. It is 10 to the negative 7, 10 to the negative something, okay? They're very, very small numerical values. Therefore, we use a pH scale to conveniently represent the acidity and basicity of a solution. So pH of a solution can be calculated by taking the negative logarithm of a concentration of hydronium ion or proton. Okay, so the concentration of proton at equilibrium is 1 times 10 to the negative 7, right? If we take negative log of this value, negative log of 1 times 10 to the negative 7, we get 7. Okay, so the pH is 7. Concentration of proton at equilibrium is this. The pH value is 7. So any acidic solution at equilibrium will have a proton concentration below 1 times 10 to the negative 7, and that gives us pH value lower than 7. It's going to be this red region over here. Okay, refer to red portion of the pH chart. The basic solution at equilibrium will have a proton concentration above 1 times 10 to the negative 7, and that gives us pH value higher than 7, refers to this blue portion of the pH chart. Okay. The significant figures for pH value is very, very important, and it can be a little confusing, so please memorize this rule. Only the digits after the decimal points are significant in a logarithm. Significant, not significant. So the whole number portion here is going to be, so whole number portion does not count when figuring out how many digits to write down. So let's say you're taking a negative log of 1.0 times 10 to negative 7. Since the original value has, how many sig fig does this have? This has 2 significant figure. Since the original value has 2 significant figures, your answer should contain 2 significant figures too. But since only the numbers in the decimal point portion is significant, you need 2 significant figures in the decimal portion. So we write 7.00. Okay, 00 gives 2 significant figures. Okay, so let's say example, calculate pH of a solution where proton concentration is 0.00100 molar. Okay, the original value has 3 significant figures. So the answer after taking the negative log of this value should have 3 significant figures too. Okay, so if you take negative log of this value, you get 3. Okay, but 3 is not enough. Okay, the original value has 3 significant figures, so the answer should contain 3 significant figures after the decimal point. So you need to put 3 zeros to match the original value's 3 significant figure. Okay, so please remember this for the exam. Incorrectly reported pH values can make you lose points. Okay. Let's try this sample exercise first. Calculate the pH values for the two solutions for sample exercise 16.5. Okay. So we're going to calculate the pH value. So we're going to have to find the negative log of the concentration of the proton. Okay, so for A, concentration of proton for A was 1.0 times 10 to the negative 12 molar. The pH is going to be negative log of 1.0 times 10 to the negative 12, which equals to negative 12.00, which is equals to 12.00. The original value had two significant figures, so you need to have two significant figures in the decimal place. For question B, the concentration of proton is 5.6 times 10 to the negative 6 molar, so the pH is going to be negative log of concentration of proton, which is 5.6 times 10 to the negative 6, which is equal to 5.25. Okay, you're going to have a longer number than this, but you only need two significant figures after the decimal point because you had two significant figures in the original value. So since negative log is a convenient way to express magnitudes of small numbers, we can also express concentrations of hydroxide and the value of Kw in p scales too. Okay, so here we're going to learn how to express hydroxide concentration and Kw values in p scales. Well, actually, let's go to this. So if you take negative log of concentration of hydroxide, it's going to be POH. If you take negative log of Kw value, it's called negative PKW. Not negative. Sorry, this negative is a mistake. Okay, please delete this negative sign. It should just be PKW. Okay. So since the equilibrium constant expression for water is Kw, and it has a formula of proton concentration or hydronium concentration times hydroxide concentration. If we take negative log of both sides, if you take negative log of this side, if you take negative log of this side, if you take negative log of both sides, you get an equation looks like this. Okay, from which we can obtain another useful expression, which is pH plus POH equals PKW, which is 14. Okay, and this is true for neutral pure water. Okay, Let's try a sample exercise about POH. Okay, I'm going to read the question. A sample of freshly pressed apple juice has a POH of 10.24. Calculate the concentration of proton. So we need to calculate concentration of proton from POH. In order to find concentration of proton, we need to find the pH. Okay, so we will use the pKw expression that we have just learned in the previous slide to find the pH value. Since we know that pH plus POH equals 14, which is Kw, we know that pH is going to be 14 minus POH. So then pH is 14.00 minus 10.24, which is the pOH value given in the question, which is equal to 3.76. So if pH is 3.76, that means negative log pH is basically negative log of concentration of proton, which is found to be equal to 3.76. Okay, so that means log of concentration of proton is negative 3.76. So then to find concentration of proton, we need to determine we need to find the anti-logarithm of negative 3.76. Okay, so it's going to be 10 to the negative 3.76 or inverse log. So practice this with your scientific calculator. I'm not sure, there should be an inverse log button somewhere in your calculator. If you can't find that button, you can simply put 10 and then raise to the power of negative 3.76. Okay, that's the value of the anti-log. If you do 10, if you raise 10 to the power of negative 3.76, it's going to equal to value of 1.7 times 10 to the negative 4 molar. Now we have successfully found the concentration of proton using the pH value. Okay, I'm going to put a star here. Practice how to solve anti-log math problems. Okay, this can be a little tricky. If you can't find the anti-log or the inverse log button on your calculator, you can simply do this. It's the same thing. This is anti-log negative 3.76. This. Okay. So how do we measure the pH value? The pH of a solution can be measured using a pH meter. pH meter. Okay. The pH meter consists of pairs of electrodes. And when these electrodes are submerged in the or inserted into the solution, a voltage is created. Okay, so depending on the levels of concentration of protons within the system, different levels of voltage is going to be created, and those voltages are going to be read by the meter. The voltage is the voltage is a unit of millivolts, but the machine is calibrated, and instead of millivolts, it gives us a value of a pH of the solution. Okay, so pH of a solution is measured by pH meter. But there's another common way to measure pH in the chemistry lab is using the indicators. Okay, these are all solid powder dyes. Okay, these are the list of all the solid powder dyes. These will change color depending on the environment. For example, when you have an acidic solution and when you add methyl red dye powder, the solution will turn red. You can see it here. Okay. When you have a basic solution, pH higher than 7, when you have basic solution and when you add methyl red powder, it's going to turn yellow. So you know that you have the solution is basic. If you use bromthymol blue dye, this dye will give different colors for acidic and basic environments compared to methyl red. When you add this dye to an acidic solution, it will turn yellow. If you add this dye to a acidic basic solution, it will turn blue. Okay, so different dyes will give you different colors for acid and basic environments. So that was a brief introduction regarding how to visualize or measure the pH value. Now we're going to move on to strong acids. So any aqueous solution with low pH value would be considered strong acids. pH values, low pH values. And these are the 7 most common strong acids. Okay, these are the 7 most common strong acids. They have very, very low pH. These acids in water, they dissociate completely. They dissociate completely and exist as ions. Okay, so and because the conjugate base of these acids are extremely weak bases, they have extremely low tendency to steal the proton and from hydronium ion to proceed the reverse reaction. Okay, so because the reaction lies heavily to the right, we just use one arrow for this equation. Okay. And another thing to note is that there are acids with 1 proton and acids with 2 protons. Acids, so here, these are the acids with 1 proton. You have 1 hydrogen, 1 hydrogen, 1 hydrogen, 1 hydrogen. 1 hydrogen, 1 hydrogen. This proton has 2 hydrogens. Okay, so acids in 1 proton in the chemical formula are called monoprotic acids. The one with 2 protons are called diprotic acid. For monoprotic acids, 1 proton from acid is donated to water and generate hydronium ion. Okay, so therefore, for monoprotic strong acids, the concentration of proton or hydronium ion is basically concentration of the acid. However, the situation is a little more, situation with diprotic acid is a little more complex, and we will learn about it later in the chapter. Okay, so for now, just know that for monoprotic strong acids, the concentration of proton or concentration of hydronium ion is basically the concentration of the acid. So any aqueous solution with high pH value would be considered strong bases. Okay, strong bases are ionic hydroxides of alkali metals such as sodium hydroxide, potassium hydroxide. Oops. I'm sorry. Sorry about that. Okay, so strong bases are ionic hydroxides. Hydroxides, ionic hydroxides with of the alkali metals such as sodium hydroxide or potassium hydroxide, and heavier alkaline earth metals such as calcium hydroxide, strontium hydroxide, barium hydroxide. Okay, and as in strong acids, these strong bases would dissociate completely in water and remain as dissociated ions too. Okay, again, dissociate completely in aqueous solution. Okay. So now that we have learned about strong acids and strong bases, we will now move on to learn about weak acids. So when weak acids are in water, the conjugate bases are slightly stronger base, okay, than in the strong acid. So because they are able to steal protons from the hydronium ion to proceed the reverse reaction, therefore the arrows in both directions are typically used. Okay, arrows in both directions. Since this is an equilibrium reaction where forward reaction and reverse reaction are occurring at the same time, we can calculate the equilibrium constant K. In this case, instead of Kc, we use Ka to denote the equilibrium constant of an ionization of an acid. Okay, so there's Kc, Kw, and now we have Ka. Okay, so the Ka is going to be concentrations of products each raised to the power equivalent to the coefficients divided by concentration reactant. Okay, each raised to the power equal to its coefficient. So note that water, pure water here is omitted from the equilibrium constant expression. We have Ka, the equation looks like this. Okay, so the magnitude of Ka shows a tendency of an acid to ionize in water. Magnitude of K shows us sorry, my iPad is keep getting frozen. Are you guys able to hear me fine?
Yeah, we can hear you.
Okay, so it's just a screen. to ionize in water. Okay, more ionization means more hydronium. More ionization means more hydronium ion concentration. Okay, so conjugate more hydronium ion concentration and more conjugate base concentrations. If higher concentrations of product, if the numerator has higher value, you will have higher Ka value, right? So does it make sense that the larger the Ka value, the stronger the acid with more ionization? Okay, so and then vice versa, for the smaller Ka value, the weaker the acid is with less ionization. Okay, so the reason why stronger acid, the larger Ka value indicates strong acid is because stronger acid will have high dissociation rate. It will have high concentration of these. High concentration of the product concentration means higher value in the numerator, then the Ka value is going to be higher. Okay, so larger Ka value is associated with stronger acid, with stronger ionization. Okay, more ionization.
Is the association here complete or incomplete?
Incomplete.
Thank you.
Partial dissociation. Okay. I'm gonna make a note here. Partial dissociation. Okay. So again, the complete dissociation is going to be for stronger acid, strong acid, and strong bases. So here are a list of few examples of weak acids. Okay. And then the Ka value here is not for the conjugate base. This Ka value is for the acids. Okay. So what can you tell from these Ka values? Okay. These Ka values for Ka values are very, very small, right? Which indicates weak acids. You do not have to remember this structural formula. Okay. But you might want to be familiar with these few names of weak acids, and you don't have to memorize the Ka value, okay? But try to be familiar with these names of the weak acids. So to compare strong acids versus weak acids, the major difference is that strong acids completely dissociate to ions. Strong acids such as hydrochloric acid in water will completely dissociate into proton and chloride ions, and they will stay this way. Okay. On the other hand, weak acids only partially dissociate into ions. This means when weak acids such as acetic acid dissolve in water, it will generate hydronium ion or proton and acetate ions, but these acetate ions are unstable. So they want to steal a proton and want to go back to the original acetic acid. So let's see. Acetic acid in water is going to dissociate. But then this acetate, it's unstable. Okay. Or in other point of view, we can say that it's slightly a stronger base than conjugate base of strong acid. Okay, so because they're unstable, they want to go back to they want to steal the proton from the hydronium ion or proton and go back to the original acid form. Okay, so the reverse reaction is likely to happen, and then what's going to happen is that it's going most of the time it's going to stay in this original acetic acid form. Okay, so in this system you will find more acetic acid molecules than the dissociated ionic forms of the acid. So we say weak acid only partially dissociate to ions. Okay, so that's the major difference between strong acids and weak acids. Okay. And then just give me 1 second. Okay, sorry about that. My screen keeps getting frozen for some reason. Okay, let me know if it's frozen or let me know if you can't see it clearly. Okay, let me know if it's blurry. Okay, so now let's do a calculation of Ka, the equilibrium constant of acid, from the pH value. Okay, so I'm going to read the question. The pH of a 0.10 molar solution of formic acid at 25 degrees Celsius is 2.38. Okay, calculate the Ka for formic acid at this temperature. So let's write the equilibrium expression for the Ka. Okay, equilibrium constant Ka is going to be, first of all, let me write out the reaction equation first. So this is the formic acid. Because it's a weak acid, you will have two arrows. This is the equation, okay? And then the equilibrium constant Ka expression is going to be product concentration divided by reactant concentration, okay? This is same as this. Okay? And then in order to calculate Ka, we need the equilibrium concentrations of all three things. Okay, so as we learned before, if you want to calculate Kc, we need concentration of products and reactants at equilibrium. Same rule applies for Ka. If you want to find Ka, you need the concentrations of ionic species and acids at equilibrium. Okay? And then another thing is that if we know pH, we can find proton concentrations at equilibrium. Okay, so the pH value is given as 2.38. pH value is given as 2.38. pH is basically negative log of concentration of proton. So then we did the similar exercise previously. In order to find concentration of proton, you just have to do the anti-log of negative 2.38, which is 4.2 times 10 to the negative 3 molar. Okay? Since we know the concentration of proton at equilibrium, this is at equilibrium. Since we know the concentration of proton at equilibrium, we also know the concentration of the conjugate base at equilibrium too. From the reaction stoichiometry, we know that for each conjugate base molecule ionizes, for each of this acid molecule ionizes, you get one proton and one equivalence of the conjugate base ion. Okay, so the concentration of HCOO minus is also going to be 4.2 times 10 to the negative 3 molar. They equal to each other. So then we can construct a table, just like we did in chapter 15. Okay, we write down everything that we already know and we leave blank for anything that we don't know. Okay, we already found the concentration of proton and conjugate base at equilibrium. We write those values here. 4.2 times 10 to the negative 3, 4.2 times 10 to the negative 3. Okay. This initial concentration was already provided in the question. Okay. In the original question, it says the pH of a 0.10 solution of formic acid. Okay, so the concentration of the initial reactant is already given as
0.10 molar. Okay, so these three are what we already know. We're going to fill in the blanks for the rest of the things that we don't know. Well, we also know that the concentration of the product is 0 initially because we don't have product in the beginning. Okay, so the initial concentration of reactant is 0.10 molar. Initial concentration of product is going to be 0 and 0 in the beginning. Okay, and then now we know, since we know the equilibrium concentration, we can basically do the math to find the change in concentration. Okay, so if you take in order to go from 0 concentration to 0 molar to 4.2 times 10 to negative 3 molar, the change that this proton experienced was positive 4.2 times 10 to negative 3 molar. The change that this conjugate base experienced was positive 4.2 times 10 to negative 3 molar. Again, just exactly same as chapter 15. You use the reaction stoichiometry to find the change in concentration of the product. Because the coefficients are 1, 1, 1, the stoichiometry is 1, 1, 1. 1 molar change in proton is equivalent to 1 mole of change of the reactant. But we put a negative sign for the reactant to indicate that you are depleting. Or using up the reactant. Okay, so now if we take 0.10 minus 4.2 times 10 to negative 3, we get the equilibrium concentration of the reactant. Okay, again, a lot of people might do 0.10 minus 4.2 times 10 to negative 3. This is incorrect. A lot of people did this in the exam, but this is incorrect. You are applying the change.
Professor, I don't know if I'm getting confused, but for the values of the reactants at equilibrium, they are the same because both of them have 1 mole, right?
What's that again?
For the equilibrium concentrations of the products, they're the same because they only have 1 mole of each, right?
They're the same. So 1 mole of this acid is going to dissociate into 1 mole of proton and 1 mole of this conjugate base. Do you agree with that?
Yes.
Yeah, so that's why if you have 1 mole of this, 1 mole of this, they're equal.
So the equilibrium concentrations would also be equal.
Correct.
Okay, thank you.
So now we have all the concentrations at equilibrium. Can we calculate Ka? Now we can calculate Ka because we do have all of the concentrations at equilibrium. Okay, so now we just have to plug in everything. It froze again. Okay, so the equilibrium constant is going to be this. You just have to plug in all the numbers. Proton concentration is 4.2 times 10 to the negative 3. Okay, and then concentration of the conjugate base is going to be 4.2 times 10 to negative 3. Concentration of the acid, because this is such a small number, we just decided to keep it as 0.10, or if you want, you can do an exact math. That's totally fine. Okay, so if you do this math, you will get a Ka value of this. Okay, so the concept of this Ka and the acid base, it's not that difficult. What's difficult is what's going to be tricky and challenging is the math part. Okay, so practice how to do the anti-log. Okay, do multiple practice, and then like these kind of questions, as you've done, as you've seen in exam 1, these type of questions will commonly appear on the exam. Okay, so be familiar with constructing a table where you are given with the given information. You need to fill in the portions that you don't know. Okay, so try to do these exercises multiple times until you're familiar with it. Okay, and then these I saw that I was going over the exam with a lot of students. They knew the concept, they understood the concept, but plugging in 10 to the negative something in the calculator was not familiar with them, so a lot of students got math errors. Okay, so be familiar with these math and calculation, how to use calculator. Okay.
Dr. Lee,
So yeah.
I have a quick question.
Mhm.
Can you go just one slide back? Can you just it's just a little fuzzy. I get it all up to where you got 4.2 times 10 to the negative 3. Can I see that real quick?
Right here.
Okay. Oh, I'm sorry. Okay, I'm starting to get it now. Hold on. Let me just
So this
thank you.
information, yeah, this information you can um um
I see it now.
mhm,
I just I dozed off for like didn't doze, but like I missed that. I skipped that. Thank you.
okay. Uh-huh. All right. I'm going to end the today's lecture here. I'm going to hang out for another 5-10 minutes just in case anybody else has questions. If not, I'll see you guys on Thursday. Okay.
Dr. Lee,
Uh-huh.
a quick question. If
Yeah.
you're finding the Ka and you already have the concentrations of the product and reactants without putting in on the ice table, do you necessarily need the ice table?
We'll say that one more time.
So for this slide, you already know the concentrations of the products, and it give you the concentration of the reactant as well. Do
Mm-hmm.
you necessarily need the ice table to find Ka?
To find Ka, what's the ice table?
The one with the
The
initial concentration, change, and equilibrium.
like this table?
Yes,
So, you're asking me whether we need to construct this table or not?
correct.
Um, yes. Yes. Because you the whole purpose here is that okay, so let me go over this with you again, okay? So within this table, what information did we just find out? Okay, the information that we already know from the question provided information is that the initial reactants concentration, right? It was given, right? And then we know that the product concentration is 0. These are the given information. And then what we have just found is concentrations of these products at equilibrium, right? So we only know these things. The other things we actually don't know yet. Okay, so we construct this table in order to find out uh, this value, this value. Okay, so this table is very necessary for you to find out the equilibrium concentration of the reactant. Okay?
Okay, thank you.
Mm-hmm. So if you don't construct this table, you might think I'm confident that I can get the equilibrium concentration of the reactant without constructing the table, but you might make mistakes on this signs if you don't construct this table.